Alright, welcome back to my channel. We're reading the book Machine Learning for Cloud and Network Engineers. Right now we're learning about data. Data is essential for AI, essential for machine learning, which is pretty much the same thing as AI. It's just more specifically talking about the basic techniques and math behind AI in a more specific way. But they're essentially interchangeable terms. So we learned about algorithms to procure the data for training. So we learned about clustering algorithms. We learned about anomaly detection just recently, which is we learned about types of clustering algorithms, hierarchical clustering. So it's all density-based clustering. We learned about specific algorithms within it. We learned about the k-means algorithm. We learned about the dbScan. Now the k-means algorithm, that's a centroid algorithm. So we also learned about centroid algorithms. We learned about rescaling the data to make values more comparable. So a way to do that is normalization, also known as min-max scaling, and standardization, also known as z-score normalization. So a lot of really advanced stuff. This book says that it's not meant to be advanced. It's meant to be intermediate at most for data science. But data science is a very math-heavy subject. So, but as I've said in my other videos, we live during the first wave of the artificial intelligence revolution, and I believe the thing that's going to separate people from being successful in the future and not is how much they can use tools like ChatGPT or whatever they choose to educate themselves. I think there's a unique advantage today in that you can learn advanced mathematics, anything you want, investing, to a really high programming, to a really fitness. You can learn how to make an exercise routine and adhere to that. Anything you want to do, you can do to the next level. You can do 10 times better than you would have been able to do it without ChatGPT. So people who are comfortable using ChatGPT, people who are able to put in that $20 a month for ChatGPT 4, or who have found a different AI that they like the results better. So U.com is the one I historically used on this channel a lot. I was really happy with that. There's a bunch of other ones. I think Hugging Face is a big AI company. So I think they would have some good offerings there as well. The other kind of big one is Perplexity, as far as I understand. This is kind of a big free one. There's Gemini. And this is another one where you can pay for some advanced access, as far as I understand. And then there's the one from Bing, which is I forget what it's called. I think it's Microsoft Copilot in Bing. So all kinds of options. If you don't want to pay the $20 for ChatGPT, I'm pretty happy with it, but I haven't tried the other ones. But you can use the free version. You don't like it, try some other free versions and then go with the one that consistently is the best. I've been pretty happy with just putting in the $20 though. Although I can afford it. I need to emphasize, if you can't afford to pay for something, usually there's a way to do it for free in an effective way, at least effective enough to get you to a point where you can work some kind of minimum wage or higher job and now you can afford to go to the next level, assuming that you're budgeting properly and you're in a surplus of earnings every month, including after contributions to like 401ks, things like that. And you can use that surplus to get the things you want. And I would even maybe argue for something like ChatGPT Premium to be something you would need, especially since it's just $20 a month. I would probably even argue LinkedIn Premium could fall into that, and honestly, dating site premiums could fall into that too, because it's really important to like having a good relationship is like one of the key factors to you know a really good life, from what I understand. So. But remember, it's only if you can afford it. The best budgeting rule is 50, 30, 20, or that's kind of the standard rule, especially if you're making average income or lower. Once you start making really high income, those values are kind of skewed. But 50% of what comes in to you in cash after things are taken out for taxes, after things are taken out for investing in 401k, after things are taken out for benefits, insurance, 50% of that needs to pay for your needs, your rent, your transportation costs, your groceries. 30% of that, anything you want in the world, you can buy it with the 30% that you have from that leftover sum. And then 20%, this is what you're just going to let pile up. You want an emergency fund with 20, with like 3 to 6 months of expenses, so that needs that you should be able to cover that just with your savings by letting that 20% build up over time. And then eventually, once that gets higher, you should do more advanced things with it. You should filter it out into extra contributions into the 401k, extra contributions into the stock market, some like side hustle, like, so that's how that works. It's just important to me that the people who have watched this channel kind of, these are the small things that is not that hard to do right, and if you do it right, it creates such a major difference between you and the people doing it wrong. All right, so let's continue reading the book. There are 3 different techniques to detect anomalies or outliers. I will briefly describe a few of them in this section, and more details will follow in the practical use cases later on in this book. And I need a quick break. I'll be right back. All right, I'm back. We can start with some basic statistical methods like z-score to identify anomalies or outliers. Z-score starts with one fundamental assumption, which is that the distribution of the sample is Gaussian. In many cases, this is a valid assumption, but we need to take this into account. Z-score seeks to estimate a deviation from the normal. The normal is considered the median of the sample. Why not the average? Because it can be skewed. Because the average is more sensitive to outliers. And precisely what we want is to detect those outliers. We want a measure that is as resistant to them as possible. The median is a good statistic for that purpose. Z-score will estimate such differences in the observation with the median and normalize with the standard deviation. So here's the equation for z-score. Z-score is equal to x minus, so z-score is difference to the product of the difference of x and the median of x divided by the standard deviation of x. And standard deviation is kind of more of a high school mean, median, mode R2. But let's get a quick review of. So give me a quick review of a mathematical concept of the standard deviation to just quick bring me up to speed.
Standard deviation is a statistical measure that quantifies the amount of variation or dispersion in a set of data values. It is commonly used to understand how spread out the data points are from the mean average for the data set. Here's a quick rundown. Mean calculation. First, calculate the mean of the data set by summing all data points and dividing by the number of points. Variance calculation. Next, subtract the mean from each data point, square the result, and sum these square differences. Divide this sum by the number of data points for a population.
And I something was wrong with my audio, so I need to hear this again. Oh, you know what? It for some reason I can't. For some reason it's not popping up. But anyways, I can read it. The standard deviation is a statistical measure that quantifies the amount of variation. So that's I guess all I need to know. But there's multiple kinds of deviations. There's the mean calculation. Oh. Show me the actual math, the symbols and the equations, and the graphs. Whatever visual element math has to describe the standard deviation, show it to me, please.
Sum underscore I equals 1, caret n x underscore I, n, mu equals n area summation I equals 1 n she, where she underscore x c are the data points and n is the number of data points. Variance, sigma squared for population, s squared for sample, measures the average of the squared differences from the mean. Sigma 2 equals I equals 1 n, she minus mu, 2 n, sigma squared equals, frac, sum underscore, I equals 1, caret n, x underscore I, mu, squared, n, sigma 2 equals n area summation I equals 1 n, she minus mu, 2 for population, where s2 equals I equals 1 n, she minus x, 2 n minus 1 squared equals, frac, sum underscore, I equals 1, caret n, x underscore I, ar, x squared, n 1, s2 equals n minus 1 n area summation I equals 1 n, she minus x, 2 for sample. Standard deviation, sigma for population, s for sample, is the square root of the variance. Sigma equals sigma 2 equals I equals 1 n, she minus mu, 2 n, sigma equals sqrd, sigma squared equals sqrd, frac, sum underscore, I equals 1, caret n, x underscore I, mu, squared, n, sigma equals sigma 2 equals n area summation I equals 1 n, she minus mu, 2 s equals s2 equals I equals 1 n, she minus x, 2 n minus 1 s equals sqrd, s squared equals sqrd, frac, sum underscore, I equals 1, caret n, x underscore I, ar, x squared, n 1, s equals s2 equals n minus 1 n area summation I equals 1 n, she minus x, 2 graphical representation of bell-shaped curve, normal distribution, is often used to represent the distribution of data. The mean is at the center of the curve, and the standard deviation determines the width of the curve. Most data points fall within one standard deviation of the mean. Let's create a graph to visualize this concept, the normal distribution curve, indicating the mean and standard deviations. Let me plot this for you.
I'd like to try something after this is done. So okay,
like
so there's an error. So let's stop this and let's try something else. So what we're gonna do is go. I would like to know more about the mathematical concept of standard deviation. Do a few things for me, please. So first, give me a assessment to gauge how much I currently know about the subject. So like give me a series of questions that I will answer, and based on my answers, procure for me a math lesson to bring me up to speed. Yeah.
That's a great approach to learning about standard deviation. Let's start by assessing your current understanding with a few questions. Answer them to the best of your ability, and based on your responses, I'll tailor a lesson to help enhance your knowledge.
Good. Okay, so for the first one, the basic definition of the standard deviation is the variation in the data. So like, how much do you deviate from the standard quantity? So like, that's not the best but it's just like it's a measure of how much the data varies. That's the basic definition. So the calculation, no, I don't know this. Sorry. The interpretation, a high standard deviation means that there's something unusual. There's outliers in the data. There's a lot of them. There's a lot. The data is wide and dispersed, and there's a lot of different data points. So a lot of variation in the data. But a low standard deviation means that the numbers are more or less the same, and the numbers that are radically different aren't all that radically different. Like, for example, if the heights of people in the room had a high standard deviation, you'd have people in the room with dwarfism who were like 4 feet tall in the same room as NBA players who were like 7 feet tall. But with a low standard deviation, you just have like average people in the room where the shortest person was like only a few inches shorter than the tallest person. For contextual application, I can think of a lot of real world examples where standard deviation might be useful. Basically anything where you want to know how much how significant or unusual it is, that something deviates. So I guess the height was a good example. Like, you want to know like how different everyone's heights in. You know what? Honestly, I'm kind of having trouble with this contextual application part. So the next part, the related concepts. Variance, not so much. Mean, yes, that's the average. That's what I'm familiar with. Normal distribution, not so much.
Thank you for your detailed answers. Based on your responses, it looks like you have a good grasp of the basic concept of standard deviation as a measure of variability in data, but you benefit from a more structured explanation on how it's calculated, along with a better understanding of related concepts such as variance and normal distribution. Let's address these areas with a tailored lesson. Math lesson on standard deviation 1. Understanding standard deviation. Standard deviation is a statistical measure that quantifies the amount of variation or dispersion in a set of data values. A low standard deviation means that the data points tend to be close to the mean average for the data set, while high standard deviation means that the data points are spread out over a wider range of values. 2. Calculating standard deviation. Here are the steps to calculate the standard deviation for a set of data. Step 1. Calculate the mean average for the data. Step 2. Subtract the mean from each data point and square the result. This gives you the squared deviations. Step 3. Add up all the squared deviations. Step 4. Divide the sum by the number of data points for a population standard deviation, or by the number of data points minus 1 for a sample standard deviation. Step 5. Take the square root of the result from step 4. This process can be summarized by the formula for the sample standard deviation SSS. S equals 1n minus 1n area summation I equals 1n, she minus x, 2 equals sqrd, frac, 1, n1, sum underscore, I equals 1, caret n, x underscore I, ar, x squared, s equals n minus 11 I equals 1n area summation n, she minus x, 2 where, n is the number of data points. She underscore xc of the data points. xar, x is the mean of the data points. 3. Related concepts. Variance. Variance is the average of the square differences from the mean. It's calculated by following steps 1 to 4 for calculating standard deviation, but without taking the square root in the final step. Variance provides a measure of how data spreads around the mean. Mean. This is the average of all the data points, calculated by summing up all the data points and then dividing by the number of points. Normal distribution. This is a type of continuous probability distribution for a real-valued random variable. The normal distribution is symmetric about its mean, and its shape is often referred to as a bell curve. The standard deviation and mean in the normal distribution define its shape and spread. 4. Real-world example of using standard deviation. Standard deviation can be useful in finance to measure the volatility of stock prices. If a stock has a high standard deviation, the prices are more spread out over a wider range, which indicates a higher volatility and potentially higher investment risk.
A stock?
Conclusion. Understanding standard deviation is crucial for interpreting data effectively, whether in research, finance, or everyday contexts. By learning how to calculate and interpret, along with related statistical concepts, you can gain a deeper insight into the variability of data and make more informed decisions. If you need any clarifications or further examples, feel free to ask.
I guess that makes sense. If a stock is always up and down and up and down and you know, then it's kind of more of a gamble than one that's always, but like you rising consistently in a more predictable way over time, I guess. But is that what standard deviation says? But anyways, the next question I have is look at the screenshot of the equation that I posted. Now, read the equation out loud in English in the clearest way possible. Oh, that's beautiful. Look at that.
The equation in the image reads as follows. S equals the square root of the sum from I equals 1 to n of the quantity x sub I minus x bar squared, all over n minus 1, where S is the symbol for sample standard deviation. The square root symbol represents the principal square root. The summation symbol, and area summation, indicates the sum of the square differences. X sub I refers to each data point in the set. X bar denotes the mean of the data points. N is the number of data points in the sample. N minus 1 in the denominator is used for calculating the sample standard deviation, which for X sub I is in the estimation of the population variance and standard deviation.
Yeah, so X bar. There we go. That's what we call it. So yeah, I think this is the key to understanding these symbols is because it's not meant to be read out loud. Like mathematics is meant to be done largely in your head rapidly as fast as possible. It's about thinking, as quickly and efficiently as you can. So we use these special symbols are used to facilitate that. But when it comes to like learning it and like understanding it, those symbols aren't so good. So what you need to know is what to call these symbols before you can just abstract them in your head and you don't have to sub-vocalize them. So S equals the square root, which we see here, of the sum. So that's what this symbol means here. From I equals 1. So the sum from. Yep, so that's what this means. And then I equals 1 right there. 2, so that's part of what this symbol means. N. Of the quantity. Oh, of the quantity. So of the quantity. Interesting. X sub I minus X bar squared all over N minus 1. Wait, what? No, it doesn't. That's not right. I don't think that's right. Let me see if that's right. Now, ChatGPT can't do math very well. And it failed to upload the image. It failed again. So now it's just completely bugging out. Yeah, this is where ChatGPT is still lacking, unfortunately. But just learning that something like this is called XBAR is pretty useful. And then that this is X sub I is pretty useful. Just knowing the language, I think helps a lot. Oh, you know what? This did. So I'm going to say assess this English sentence that describes the equation in the screenshot for accuracy. Make corrections if needed. I think this is one of the places where ChatGPT just doesn't work. So we'll try it in a new one here. Oh, it
sentence you
is?
provided is indeed a correct verbal description of the formula for the sample standard deviation in the image. It correctly identifies each part of the formula. S is the sample standard deviation. The square root refers to the radical at the beginning. The sum from I equals 1 to n indicates the summation notation. The quantity x sub I minus x bar squared refers to each individual value, x sub I minus the sample mean, x bar squared. All over n minus 1 denotes that the summation is divided by the sample size minus 1, which is a characteristic of the sample standard deviation formula. The formula represents the process of calculating the sample standard deviation, which measures the amount of variation or dispersion in a set of values.
I feel like that's not right. I don't know. Just something doesn't feel right about that. The all over n minus 1 thing is what, because it's like, wait, where does it plug in? It plugs in. Does this mean that it plugs into the n? I thought the n was. Why are there two n's here? Are these representing the same n's, or I feel like they're. I feel like the. So I feel like why I'm so confused about this is because we have the letter n in the equation twice, and I feel like they're not representing the same thing when they're used. The first instance of n is used to mean to plug in the parentheses part of the equation to the right into that instance of n. But the second instance of n is an abstract indicator that means as the value of I increases continuously to whichever value you plug in. So like, is that true that the two instances of the letter n represent two different mathematical concepts? That's why I'm confused if that's the case.
I understand the confusion.
Oh, it does?
The letter n and n is indeed used twice in the equation, but it represents the same mathematical concept in both instances. Here's a breakdown to clarify. The first instance of n and n is at the bottom of the fraction, n minus 1 and 1 n minus 1. Here, n and n represents the total number of observations in your sample. The reason we use n minus 1 and 1 n minus 1 instead of just n and n is to correct for the bias in the estimation of the population variance and standard deviation. This is known as Bessel's correction. The second instance of n and n is in the upper limit of the summation symbol sigma, sigma, sigma. This tells you to sum the square deviations of each observation from the mean, she minus x2, x underscore I, ar, x squared, she minus x2, for all observations from I equals 1, I equals 1, I equals 1, I equals n equals n. In this context, n and n again refers to the total number of observations in the sample. So in both instances, n and n refers to the same thing, the total number of observations or data points in the sample. It may help to think of n and n as a placeholder for a specific number. For instance, if you have 10 data points, n and n would be 10 in both places it is used in the equation.
All right. Anyways, I'm satisfied with that. Let's move on. So the higher z-score is in absolute terms, the more x deviates from the normal for that metric. It is usually considered that anything beyond 3, so larger than 3 or lower than negative 3, is an outlier. It is usually considered that anything beyond 3, so larger than 3 and lower than negative 3, is an outlier, and that's written there twice for some reason. Yeah, that's the same sentence. It is usually considered that anything beyond 3, and it says that here as well. It is usually considered that anything beyond 3, and then it says in the parentheses, so larger than 3 or lower than 3, and it says the same thing here. So larger than 3 and lower than 3, and then the last part is an outlier, and it says that. So we can see there's a duplicate sentence here on this page. We could then use this technique for the example of the memory utilization on the top of rack devices and detect those that deviate from the normal 20 to 25%. Of course, we are assuming here that memory follows a Gaussian distribution. We will evaluate other algorithms if that is not the case. So here's our graph here for we've got memory utilization here. Now we've got CPU utilization. So we've got this clusters of the data. This is the normal data that we expect to see here. And we've got some outliers here. Some things are going wrong, presumably, or something's happening where there's more memory utilization, especially than we were expecting. And these are also outliers here as well. There's a far more CPU utilization than we're expecting. However, given that we are looking at z-score, we can also use it to detect anomalies in a time series, the traffic example above. How do we determine the normal in this case? The normal needs to be determined based on the past history of the metric, which is all we know. Therefore, we can compute a moving median of the past n observations and also compute a moving standard deviation for the same n observations, and use the same technique using the z-score formula. So there we go, z-score formula. Everything. So this is the z-score formula. I don't know if we've. No, this is a little bit different from the. Yeah, this is the first time we're introduced to the z-score formula. I thought we talked about z-score before, but I'm not sure if we were shown the formula for it. I'm pretty sure z-score was brought up before. You know what? No, this is the first time we're talking about z-score. So let's jump ahead to the bookmark and move on to the next section. So, okay, and it'll explain the formula here. So the formula means where x, and remember, we have the language now. And let's do that with this equation as well. So we're going to use that same prompt that we used here before. And the prompt is going to be, look at the screenshot of the equation posted above. Now read the equation out loud in English in the clearest way possible. And even if it doesn't do it correctly, that's okay, because we just want to know how to say the terms. Sorry, I sometimes in the mornings I get really gaggy just out of nowhere. It's kind of rare. Okay. Okay, so let's hear the common English for this.
The equation reads as follows. Z-score subscript raw equals the raw score x subscript raw minus the median score x subscript median, all over the standard deviation x subscript STD.
Okay, so subscript. That's an important word to know. So let's read it. So x subscript t now equals the value of the observation in t equals now. So if we fill in the t now, and we have to fill it in there in order to get the z-score, then x subscript median of n, median of the metric for the past n observations, x subscore standard of n, standard deviation of n, the standard deviation of the metric for past n observations. If the absolute value of z-score is greater than 3, that means, and remember, we're choosing 3 because this is a Why are we choosing 3? So that means that xt now is anomalous. Um, Tell me. So, tell me about the idea of the z-score absolute value being greater than 3. Is that somehow inherently coupled with this z-score formula, or like a part of it in any way? Oh, it's part
The
of
concept of a
the
z-score having an absolute
example.
value greater than 3 is not inherent to the formula itself, but
Yeah, I think it's part of the example. So let's try to understand where that number 3 is coming from. Where did the number? Oh, well, the number 3 was first brought up there. No, three is part of the formula. No, I think you're wrong about this, because I think 3 is the deviation. So like if it's in a standard deviation of 3 or greater, then that means that you're dealing with outliers. So I think the number 3 is essential to this equation, because if it's 3 or greater, then it means that you're dealing with outliers.
I understand where you're coming from. The number 3 does hold particular significance in statistics, especially in relation to the standard normal distribution and the identification of outliers, but it's not a component of the z-score formula itself.
Why?
Let me clarify. The z-score formula, z equals x raw minus x median x equals frac x underscore x raw. X underscore x median x underscore x std, z equals x std x raw minus x median simply standardizes an individual data point x raw x underscore x raw by subtracting the median, or mean in traditional z-score calculations, and dividing by the standard deviation. This process converts the data point to a z-score, which tells us how many standard deviations away from the mean or median the original value is. The number 3 is indeed often associated with z-scores in the context of the empirical rule, as previously mentioned. The empirical rule, or the 68959.9.7 rule, states that for a normal distribution, approximately 68% of data falls within one standard deviation of the mean. About 95% of data falls within 2 standard deviations of the mean. Around 99.7% of data falls within 3 standard deviations of the mean. Therefore, when a z-score is beyond 3 or minus 3, an absolute value greater than 3 is beyond the 99.7% confidence interval for a normal distribution, and such a data point is often considered an outlier. This is because it is exceptionally uncommon for a data point to be this far from the mean if the data is normally distributed. To sum up, the importance of the number 3 in relation to z-scores is about interpretation within the context of a normal distribution. That is an intrinsic part of the z-score calculation itself. The calculation will produce a z-score that indicates how many standard deviations away from the mean or median value is, regardless of whether that z-score is less than, equal to, or greater than 3. This image displays the normal distribution curve, also known as the bell curve, with percentages that represent the amount of data within each section as defined by the standard deviation from the mean. From the center of the curve, which is at 0 standard deviations, the mean of the data, the curve is sectioned in ranges that are 1, 2, and 3 standard deviations away from the mean on both sides. The percentages are as follows: 34.1% of data falls within 1 standard deviation above the mean, and another 34.1% within 1 standard deviation below the mean. That's a total of 68.2% of data within the first standard deviation from the mean. An additional 13.6% of data falls between 1 and 2 standard deviations above the mean, and another 13.6% between 1 and 2 standard deviations below the mean. This means 95.4%, 68.2% plus 27.2% of data falls within 2 standard deviations from the mean. There's 2.1% of data between 2 and 3 standard deviations above the mean, and another 2.1% between 2 and 3 standard deviations below the mean. This adds up to 99.7% of data within 3 standard deviations from the mean. In the image, there is a definition of terms related to a z-score calculation and a statement followed by a line graph. Definitions: x now x underscore x now represents the value of the observation at the current time point, t equals now. X median x underscore x median, and x median is the median of the metric for the past n observations. X std and x underscore x std, and x stdn is the standard deviation of the metric for the past n observations. Statement: if the absolute value of the z-score is greater than 3, this indicates that the observation x now underscore x now is anomalous. Graph: the graph seems to depict a time series of data points with certain points marked to indicate anomalies. These anomalies are likely the points where the z-score exceeds the absolute value of 3, which is a common criterion for defining outliers in many fields. This methodology uses the median and the standard deviation from a set of past observations to standardize the current observation and determine if it is an outlier, i.e., significantly different from what's expected. It aligns with the statistical concept that values which are more than 3 standard deviations away from the median are rare and often considered anomalies within a dataset, assuming the data follows a roughly normal distribution.
So are all of those yellow points anomalous, or just the ones that are branched off from the line and not the ones directly on it? See, ChatGPT isn't it can't 100x you, it can 10x you, but it can't 100x you.
In the graph provided, it appears that the yellow points are used to indicate potential anomalies. Based on the statement that an anomaly is defined as an observation where the absolute value of a z-score is greater than 3, we would look for points that have a significant deviation from the median trend. The yellow points directly on the line are likely to have points that are not anomalous. They follow the expected trend of the data. The yellow points that are branched off from the line, those that deviate substantially from the median trend line, are the ones likely considered anomalous.
Oh, okay. All right.
These are the points where the distance from the median is large enough to result in a z-score greater than 3 in absolute value.
See, I don't know if it's right,
It's important
though.
to note that without the actual data or z-scores, we cannot say with certainty which points are anomalous, but typically in such graphs, anomalous data points are marked in a way that distinguishes them clearly from the rest, often with a different symbol or color. If the yellow points that are branched off are the only ones highlighted as such, they would be the ones considered anomalous.
All right. Okay, thank you. Now assess. Oh, sorry. Never mind. I wanted to assess. Yeah, assessment. So. When it comes to learning more about math and mathematical concepts and developing a mathematical intuition, assign a letter grade to the strategy that I attempted here, which was to ask for ChatGPT, ask this AI program to give me an assessment to gauge how much I currently know about the subject, and then to give me a math lesson based on my answers to the assessment. Assign a letter grade to that strategy, evaluate other sorts of strategy, and recommend to me the best strategy for learning advanced mathematics.
Assigning letter grade to your strategy is a subjective task, but I'll provide an evaluation based on educational principles. Strategy, self-assessment, and tailored learning DII. Grade, A. Evaluation, adaptive learning. Your strategy involves self-assessment, which is a crucial part of adaptive learning. It helps the AI understand your current level and tailor the lesson accordingly. This is a hallmark of effective teaching. Active engagement. Asking for an assessment requires active engagement, which is a strong indicator of effective learning. You're not passively receiving information, you're actively seeking it. Immediate feedback. The AI can provide immediate feedback and clarification, a key component of effective learning. Targeted instruction. The lessons can be targeted to address specific gaps in knowledge, avoiding redundancy and making the learning process more efficient. Areas for improvement. Depth of learning. An AI's explanation can sometimes lack the depth and nuance a human teacher or a comprehensive textbook might provide.
True.
Problem-solving practice. Mathematics is learned best by doing. To develop a strong mathematical intuition, extensive practice with problems is necessary, and this strategy should incorporate more hands-on problem-solving.
True.
Peer interaction. Learning from peers and engaging in discussions can enhance understanding, something this strategy doesn't inherently provide. Other strategies to consider. 1. Problem sets in practice. Regularly solving a variety of problems enhances problem-solving skills and mathematical intuition. Online courses and lectures. They offer structured learning from professionals and often include problem sets. Mathematical software. Tools like MATLAB or Mathematica can provide practical experience with mathematical concepts. Study groups. Collaborative learning can deepen understanding and provide multiple perspectives on a problem. Tutoring. Personalized instruction from a tutor can offer the benefits of tailored learning with added depth and interaction. Recommendation for learning advanced mathematics. Use a blend of strategies. Start with self-assessment to gauge your understanding as you bend. Follow structured courses or textbooks for comprehensive knowledge. Engage in problem solving regularly and use AI or tutoring for targeted assistance. Discuss concepts with peers or in study groups to broaden your understanding and discover new perspectives. Use mathematical software to gain practical experience with abstract concepts. Combining these approaches will give you a more rounded and robust mathematical education, allowing you to develop both your knowledge and your intuition.
Okay, now let's say that, like, my experience with mathematics was years ago, before, like, you know, Python even. Like, I guess Python was made in 1991, so, like, when I learned math, Python would have existed, but it wouldn't have been used, you know, like the modern, like, computer and internet revolution happened as I was growing up. So, like, you know, I think of math a lot as, like, paper and pencil, and I want to reframe my intuitions with math to think of it from a code first perspective. So, like, if I think about something in math, I instantly think, how would this look in Python or in Mathematica or in whatever language is the most appropriate to work with the math. So like I instantly one-to-one map my understanding of math with my understanding of things like programming. How can I kind of reshape my experiences and thoughts about math to get away from like, you know, grade school paper and pencil, like failing tests and stuff like that, and to get towards doing valuable things with computers instead. Assess this instinct that I have and this desire that I have, assign a letter grade to it, tell me other ways I could be thinking, and help me improve as a person. Yeah, I think that's solid.
Strategy. Reframing mathematical intuition with a coding first perspective.
That's what I want,
Grade.
yeah.
A. Evaluation. Contemporary relevance. Coding is an integral part of modern mathematical application. Your instinct to map mathematical understanding to programming is highly relevant to today's technology-driven world.
That's what I want.
Practical application. Code first thinking is hands-on and results in a tangible outcome, which reinforces learning and provides immediate feedback.
That's what I want.
Cross-disciplinary skills. This approach not only strengthens your mathematical intuition, but also develops your programming skills, providing a dual benefit. Problem-solving focus. Coding often requires a problem-solving mindset, which is essential in mathematics. Applying code to math problems can foster deeper understanding and innovative solutions. Areas for improvement. Balanced learning. While focusing on coding is beneficial, it's also important to retain the ability to solve problems without a computer, as it strengthens mental computation and traditional problem-solving techniques.
Yeah.
Algorithmic thinking. Learning to think in algorithms or step-by-step procedures can be as important as coding itself and should not be neglected. Understanding foundations. A strong grasp of foundational concepts without the aid of computers ensures that your skills are versatile and not solely reliant on technology. Other ways to think about mathematical learning. 1. Open source contribution. Contribute to open source mathematical software. This provides practical experience and collaboration with other developers.
They skipped this
Competitive
one.
programming. Engage in competitive programming, which often involves mathematical problem-solving skills. Contribute to educational software. Work on projects that create educational tools for learning mathematics, which can reinforce your own understanding while helping others. Cross-disciplinary projects. Apply mathematical programming to fields like data science, machine learning, or physics, which can give a broader purpose and context to your learning. Recommendation for reframing your perspective. Immerse yourself in code. Start working on small projects that involve mathematical problems you're interested in. As you grow more comfortable, scale up the complexity of the problems. Study computational mathematics. Delve into subjects that inherently blend math and programming, like numerical methods, algorithms, or data structures. Use visual tools. Take advantage of tools that provide visual feedback, like Jupyter Notebooks, which can help in understanding abstract concepts through visual representation. Peer learning. Work with someone who has a coding-first mindset for mathematics, allowing for knowledge and intuition exchange. Educational shift. Transition from seeing mathematics as a subject with right or wrong answers, like in a test, to viewing it as a tool for
Name the top 10 people in the world who have a code-first mindset towards mathematics.
Naming the top 10 people globally with a code-first mindset toward mathematics is challenging, as this is not a standard
Yeah,
category.
this is who I would have thought.
Many contributing in different ways. However, I can highlight several prominent figures who are known for integrating programming and computational methods with mathematics.
Let's do this. Let's
Note that
make
this is
sure
not a
they're
ranking, but rather a snapshot of diverse contributors to the field. Stephen Wolfram, the creator of Mathematica and the Wolfram language, founder and CEO of Wolfram Research.
Let's make sure I have
A computer
this
scientist
list
and
of
emeritus professor
people
known for his work on algorithm analysis and for writing The Art of Computer Programming.
on my LinkedIn.
Guido van Rossum, the creator of Python, a language heavily used in scientific computing and mathematics. Leslie Lamport, a computer scientist known for his work on LaTeX, a document preparation system widely used for typesetting mathematical and scientific papers. Tim Berners-Lee, well known for inventing the World Wide Web, he has also contributed to web standards that are fundamental to data sharing and analysis in scientific research, which includes mathematical applications. Gilbert Strain, a mathematician with contributions to finite element theory, the calculus of variations, and wavelet analysis, and who has promoted computational approaches through his textbooks and lectures. Andrew Ng, co-founder of Coursera and a researcher with contributions in machine learning, a field heavily intertwined with advanced mathematics and programming. Grigori Perelman, although he is not known specifically for a code-first mindset, his work on the Poincare conjecture had profound implications for computational mathematics. Terence Dow, an extraordinarily prolific mathematician with contributions across a broad spectrum of mathematics, who also advocates for the use of computational tools in research. Peter Norvig, a computer scientist with contributions to artificial intelligence, he's also co-author of Artificial Intelligence, a modern approach which integrates a lot of mathematical concepts with programming. This list includes individuals who have made significant contributions to fields that embody a code-first approach to mathematical thinking, such as computational mathematics, programming language development, and the intersection of mathematics with computer science. They represent a range of sectors including academia, industry, and education technology. Keep in mind that there are many others who are also advancing these fields in important ways, including educators, researchers, and practitioners who may not be as widely recognized.
Okay, so Donald Knuth is doesn't have LinkedIn. So these people will all have it. You know, these are younger people. I can't follow him, so I guess I'll connect with him. I don't know if he would want to. I feel like because connecting, like, he sees everything coming up on my stream. Is this? I can't tell who these people are. I don't think this is that person. No, it's not. I mean, I don't have to add them all. It's just, this is the kind of thing I encourage people to do watching my channel. I don't think they all have John, Sir Timothy. Oh, it's Timothy. No, yeah, right. Sir Timothy John Berners-Lee. See, I'll follow. See, the thing is, like, the goal of this is to get good updates in my feed. So, like, if they're gonna tell me, like, who important people are, I'm good with that. Oh yeah, this is him. Oh, he's retired. Yeah, so, like, I don't have to follow the specific person. I just following people who talk about these people is probably a good step. This is okay. That's more of a. I think the younger people have LinkedIn. Oh yeah. Oh, this guy. Yeah, I've heard of this guy. This guy's pretty. This guy is. The thing is, I'm afraid I'll get misinformation from some if I follow these. Terrence Tao, definitely heard of him. I'm sure he definitely has LinkedIn. Yeah, this is him. Yeah, he got like a PhD in 1992, and he was born in like 75. I guess that's not. Wait. Oh, it is. A PhD at 17 is extraordinary. All right, and then one more person, and we'll keep reading the book. This is kind of the slow part. There's just a lot to go over. I think this is the. So this is a person who, yeah, artificial intelligence, a modern approach. That looks good. That might be a good one for. That might be a good one for later. All right, I think this is him. He's at Stanford. Let's see here, Stanford. It doesn't say. It's probably fine. Unless. No. Okay. All right. So. Yeah, and it's a textbook, so what is it, like $200? All right. So, yeah, let's keep going. Let us suppose that the sample we want to detect anomalies in does not follow a Gaussian distribution. Therefore, the methods above cannot be applied. We need more sophisticated techniques to identify anomalous or outlying behavior from those samples. For unvariate or and multivariate non-time series cases. Use case number 2 above, we can use clustering techniques that can both identify clusters and point to outliers, such as dbScan. There are also other algorithms more specifically intended to detect outliers, such as isolation forest algorithm intended to detect outliers. This is an example of a very interesting technique in machine learning called ensembles. Multiple instances of an algorithm, and the outcome is the aggregate view of all of them, sum, mean, etc. Isolation forest tries to isolate observations in a sample by randomly setting thresholds in the different planes. For simplicity, we will only show planes x and y. That will split them into 2. So here we go. Here's the isolation forest. Same graph as before, but now we're splitting it into 2 planes, and we have a decision tree here. In the diagram, we see how the first random plane has separated the x-axis in 2. In this case, the outlier is isolated. This is reflected in the decision tree since one of these decision branches has only one element, whereas the other still has all the remaining observations. The goal of the algorithm is to progressively isolate all samples by sequentially splitting all areas of the space with planes. Intuitively, we can see that outliers tend to be isolated faster on average because they are inherently more separated from other observations than others. In the following example, the plane 1 separated the y-axis in 2 areas, which both contain a number of observations. In step 2, though, the new split, now in x-axis, gets our outlier observation isolated. So now we split it into another plane. We've got it labeled here, 1 and 2, and the outlier is even more isolated, I guess. I don't know. I don't think I understood that right. But continuing on, the algorithm will continue until all observations are isolated in their own spaces. Remember, the algorithm does not know which outliers are in advance. Therefore, it needs to continue until all elements are isolated. So it's going to go through and there are no outliers here. Here's there an outlier. I think that's how that works. I'm a little bit lost. So now it's splitting everything into a plane, it looks like. At the end of the process, the more dense areas in observations will have many planes and splits. So we can see that here, lots of planes and splits. It means the tree will be deeper in that area in order to be able to separate all of them. On the other hand, much fewer divisions were likely needed to be isolated for the outliers. Since plane divisions happen randomly, it could still happen for a particular tree where the outlier is isolated very deep on the tree. Therefore, the algorithm does not use the output of a particular tree, but the aggregate result of many trees, hence a forest. It will compute an average as the isolation score, the layer of the tree at which a particular observation is isolated. Observations with a lower isolation score are the candidates to be outliers. Other frequent algorithms for outlier detection are local outlier factor and one-class support vector machines. There are many others. We will apply some of these algorithms in the practical section of the book. Now, let's consider the time series use case. Very frequently, a primary statistical model, as the one explained earlier, z-score over moving average or median, may not be good enough. The time series could show certain seasonal behaviors that should be considered to determine if the next value is anomalous. A moving average can capture the local dynamics of the short-term past. However, we need mechanisms to learn deeper from past longer-term behaviors, which may include seasonality, daily patterns, weekly patterns, yearly patterns, etc., and trends. One approach to address this could be to somehow able to understand the different time contexts of the metric and apply anomaly detection for each separately. If we know a metric has a daily seasonality, it has a repeating pattern across days. Therefore, it behaves similarly every day at 1 a.m., but the behavior within a particular day between 1 a.m. and 3 p.m. is different. We could split the day, for example, into 30-minute periods, analyze every corresponding 30-minute slot across many past days, and perform anomaly detection based not only on the past moving average, but also on the behavior observed in the 30 minutes time slot historically. This allows our anomaly detection for the time series to capture the current dynamics and the expected baseline given the past history. The normal detection within each time slot could be done using different techniques. Starting with the basic average calculation to using a clustering algorithm such as k-means that will allow capturing more complex patterns of normality and identifying outliers within that context slot. The below is just an example of how clustering mechanisms can be used to detect anomalies over a time series, capturing seasonal behaviors. Anomaly detection over time series is a big field with multiple approaches and algorithms. So, simple graph here. Let's see what ChatGPT has to say about this. And advance the bookmark.
This is a schematic representation of an anomaly detection process in a time series dataset. The top part of the image shows a waveform indicating the variation of some metric over time. Specific time intervals are highlighted, and from those, buckets are created for further analysis, as indicated by the arrows pointing down to the buckets labeled with specific times such as 1 p.m. to 1:30 p.m. and 12 a.m. to 12:30 a.m. Below this, the k-means algorithm, a type of clustering method, is used to identify clusters with normal value ranges represented by box plots. Box plots are a standardized way of displaying the distribution of data based on a 5-number summary: minimum, first quartile, Q1, median, third quartile, Q3, and maximum. An outlier, which is an observation point that is distant from other observations, is detected as shown by the arrow pointing to a box plot where the data point lies outside the whiskers of the plot, suggesting it is outside the typical range of values. The visualization is a conceptual overview of using statistical methods to process and analyze time series data to find patterns or anomalies, which can be critical for various applications like fraud detection, system health monitoring, or demand forecasting.
That was really useful. I don't even think I would have noticed that these are arrows without that. All right, so I think this is probably a good stopping point. So we're going now that we looked at that graph. We're gonna learn more about example techniques. So I'll save that for the next. I would like to get to here, but I don't know if I can do that in like 5 minutes. You know what? I can't do that in 5 minutes. It's just too dense. So that's it for this video. Thanks for watching. And well, let me make sure that I have this finished here. So I'm gonna hide the notebook, show it again, and go to the out of the older bookmarks and delete them, and make sure I'm skipped ahead to the current one on page 41. There we go. So that's it for this video. Thanks for watching. See you in the next one.